All right, so let's try this frame problem. And I wanted to work this one because we're only interested in finding the slope at a point. We've done some with displacement. Let's do one with slope. Compared to the previous one we did, you'll notice that this is going to have three elements to deal with. So we're going to have to worry about the energy from A to B, B to C, C to D. Also notice that the moment of inertia values in the columns are 600, but the beam is 900. So we'll have to keep track of that too. Also, we have a load right here in the middle, so we'll have to write two equations for the real moment up here from B to C. So let's start with that. No matter where we cut the structure, we're going to end up with having to include the supports. So I think it's probably a wise choice to start off by finding the supports. So at A, I'll assume that there is a reaction up at A and B. It looks like a fixed connection, but that's actually a pin. So that would be, you would have dy and dx. So let's find those reactions. So what I'm going to do first is I'm going to sum moments about D. That would eliminate dx and dy, and I should be able to find ay in terms of the load. So let's start up here.
Are we assuming D's a pin?
Yeah.
Or is it drawn as
It kind of is. It's really hard to see, but if you looked close, you'd see that there's just a little flange right towards the center. And plus, if it were a fixed connection, this would be an indeterminate problem. We couldn't solve it. But if you're interested in those problems, in the spring of 2019, you would be encouraged to take our Structures 2 course. Hopefully we'll see you all there. So I know you all want to be structural engineers, right? The overwhelming silence, I take it as yes. Okay, so we're going to sum moments at D, and we're going to set it equal to 0 for equilibrium. So about D, my 12 kip force creates positive moment. So force is 12. The distance from D to the line of action of the force is 5 feet. And then AY creates negative moment at a distance of 10 feet. So it looks like AY is equal to 6 kips. Then I'm going to sum forces in the vertical direction. I'll call that Y. And set that equal to 0. And I'll assume up is positive. So looking at my free body diagram of the structure, I have AY acting up. I have dy acting up, and my applied load 12 is acting down. So if I know AY and I plug it in there, it's not too difficult to see that dy is also 6 kips. And that's not a surprising result. You'll notice that the load is applied right in the middle. And with no other loads applied, you'd expect the reactions to take basically half the load. And they have. And just to finish this off, I'm going to sum forces in the x direction equal to 0. I will assume to the right is positive. And the only force I have is dx, so it's 0. So I found my reactions. So now I got to go through and find all my real moments. So I'm going to cut this structure here between A and B, and I have to decide whether I want to work the bottom or all this other piece. I don't think there's a lot of problem there. I think you're going to want to work this part of the structure. Equally, if you look over here at DC and you cut that somewhere, again, your choice is this segment or this big kind of U-shaped thing. Again, I think you're going to see that that's probably the easiest way to go with that. we'll come back and do all this. And then up here between B and C, I've got to look at a moment for the first 5 feet and a different moment for the second 5 feet. Now you might remember this looks very similar to an example problem we did back a couple weeks ago. And in that problem, we cut it here and we looked at this little smaller L segment to the left, which would then only include the reaction force. And on the other side, we cut it, say, here, and again we only looked at the smaller L segment that only include this reaction. And you'll see they'll be very similar. So with that all set up, what I want to try to do now is find the moments due to the real force. And I won't necessarily take these in order. I will start with AB. So if I start with section AB first, my free body diagram looks like this. I have my reaction acting up at AY, which we solved for. That's 6 kips. And then I'm going to assume my moment behaves this way. And I'm going to also make an assumption that my coordinate system varies up, and I'll call that Y. Now, I'm only looking for moment right now. I don't think it's hard to see that the only force on the structure passes right through my cut. It's not going to create any moment. If you don't see that, quickly write the equation, sum the moments at the cut, set it equal to 0, and what are you going to have? All you're going to have is the internal moment, and that's it. About the cut surface here, 6 passes through it, creates no moment. So the moment there is 0. So that means when I go to do my virtual system, I'm not even going to bother with finding the virtual moment here, because I'm going to multiply it by 0 and then integrate it. So it's not going to create any energy. If I also look at its mate here on the right side, this would be this was AB. If I come over here and do CD, you'll notice I have a similar situation. There's my lower portion. At D, I have a reaction. It's also 6 kips. I'll assume my moment behaves this way. This will be the moment at CD. And again, I'll assume a coordinate system that starts from the bottom and goes up, say Y. But again, when I sum moments there, about the cut I just made, and set it equal to 0, I only have one value. It's the moment at CD. So it's got to be 0. Okay? So the only real moments that are going to affect my calculation are up here. So basically it's almost turned into a beam problem.
How did you know that it was bending to positive is going to...
Oh, I just assumed. You can assume any direction you want. But once you make this assumption, in the virtual system, it has to be the same. You can't change directions. So let me slide over here and let's do section BC. So in that particular one, the free body diagram, looks a little different. My drawing got a little out of whack. I'm sorry about that. So I still have my reaction down here at the bottom. That's 6 kips. The height of this thing is 12. And I'm going to assume that my X goes from left to right. And I'm going to assume, probably most of you will see this, this looks like more like a positive moment that we've seen before in our beam work. And I'm just going to solve for the moment. So again, I will sum moments at the cut. make it equal to 0. And what do we have? Well, this moment is positive, so that's the moment in BC. Then I got this 6 kip force. My reaction now does create moment. And about the cut, that would be negative, so that's 6 kips, and the distance is x. So it's pretty easy to see that the moment at BC is 6x. Yeah.
So are we looking at the whole left side up to that cut now?
We're looking at the left side, this whole left side.
And that's because we know that there's no moment at both sides.
Well, I just cut it here, and I look at everything that's on the structure on the left side.
Oh, not to the next one.
Not the right side.
No, I mean like cut it, come down, have another cut.
No. This was the cut when I was looking for the moment in DC. I mean AB. I'm not going to stop it there. Well, you could, but then you'd have to include the moment that you've computed here, which is 0. Wouldn't make any difference. Because you'll notice that in this case, it doesn't matter what 12 is. 12 doesn't figure into the problem at all. But that's just for this particular problem. It's not a pattern. The pattern you should see is that when you make a cut and you say go left, you have to take everything that's on the left-hand side and see how that affects the moment. So we're going to go now. This is BC, but really it's not all of BC, right? It's like just for the first, 5 feet. So I'll call that BC1. So the other one will be the other side of BC. I'll call that BC2. In that case, when I make my cut here, I want to look at all the right-hand side. So in that case, my free body diagram might look something like this. And again, at the bottom, I have a 6 kip force. That's the reaction dy. And now I'm going to make a coordinate system from the right to the left and call that x1. And then I'll put my positive moment there. And I'm going to solve for that moment. I'm going to do that by summing moments at my cut. Make sure it's in equilibrium, equal to 0, and I'm going to use right-hand rule. So with that, I look at my moment internally, and in this sign convention, that's going to be a negative moment. And then about the cut, the 6 kip creates positive moment. So positive 6 kips times a moment arm of x1. So when I solve for my moment in this segment, it's 6x1. So now I have all the virtual stuff that all the real stuff that I need. And the interesting thing about this problem is you'll notice here that the columns A to B, D to C are contributing no bending energy to the displacement or the slope. All right, so I've run out of paper on this particular one, so let me peel that off and get you another one that we can translate to. And let's group these. Oops, we have to do the virtual work now. Sorry, I'm having a little bit of infrastructure issue. Kind of like the country. Nothing. I get nothing from you guys. All right, anyway, so let's do the virtual energy. So what would be the virtual system that we're going to look at? But remember, the problem wants the slope at A. So what do? I go to A, and what do I apply? A moment. Right? For slope, you apply moment. For displacement, you apply force. So I'm going to redraw my system. A little bit smaller system. And to make it easier to see, I am going to apply a moment here at A. Now, how am I going to do that? Well, I'm going to assume slope to be positive. So a positive slope here would be rotation clockwise. And what causes clockwise rotation is a couple that looks like that. Now, based on that, I'm still going to have a reaction at A reaction at D in both the X and Y directions. And that is the only load on my virtual system. No real load there. So the first thing I have to do is find these reactions. So I'll sum moments. Just like I did at the very beginning of the problem, I'll sum moments at D. Make sure in equilibrium using right-hand rule. So when I'm summing moments at D, I have the applied moment, which ends up being negative. And I have the moment due to the reaction AY about B, which also tends to be negative, times the distance, which in this case is 10 feet. So it looks like AY is going to be negative 1 over 10. And that kind of makes sense. If you look at D, this unit couple is trying to cause the structure to rotate clockwise. So AY needs to be pulling down to balance it. I said clockwise, I meant counterclockwise. And AY needs to be down to pull it clockwise. Is that right? No, I got it backwards. I said it right the first time, didn't I? Yeah. This is moving clockwise, and AY has to turn around and move it counterclockwise. So I'll get it right. So to finish this, I'll sum my forces in the Y direction. Again, make sure I'm in equilibrium. I'll assume up is positive. So I have AY acting up plus DY acting up, and that's it. So that means that DY has to be positive 1 over 10. And just to make sure this is all nice and tidy, we'll go ahead and sum forces in the X direction. And all we have is dx, so it's 0. So I have my reaction. Now before we cut, and let's go ahead and talk about that. Remember that we already assumed in our previous part of the problem cut surfaces and directions for all of these. And I want to remind you that we found the real moment to be 0 in AB and CD. So I'm not going to worry about those. Right? So I'm only going to worry about the cuts I made in BC, which is I cut it here, went to the left, and on the right side of the load, I cut it here and went to the right. So let's redo those cuts. Just to show you, I'll redraw them here. I want to go that way, and I'll cut here, and I want to go that way. You know something? Nope, that's right. Sorry, had a little brain fart. Had a misfire. My electricity in my neurons generated a chemical soup response that was inappropriate. So I'm back. All right, huh? Yeah. It's actually interesting. I'm reading a book about the debate between whether your brain is electrical or chemical. They called it the shock and the soup people. So if you were an electrical guy, you were a shock. If you were a chemical guy, you were a soup. And they argued about this for many decades. Many Nobel Prizes were given for various people who came first, but it turns out it's both. But the actual communication is neurotransmitters, right? All those dopamines, whatever means, gamma means, all those other things that drive your brain. But they're all electrically driven. So it's kind of interesting. Well, I found it interesting. You may not. Well, you may not. Your brain right now may be thinking, what the hell is he talking about? But while you're doing that, you are actually doing electrical and chemical exchanges, which is kind of nice. Ironic in some sense. Has nothing to do with the problem. But I just felt that the way you were looking, that you needed some segue.
Yeah.
Is that, you feeling better now?
I'm glad you explained it.
Yeah, I don't have any idea what I'm saying, but... All right. So let's look at this section of BC. So I'm going to draw a little free body diagram of that. So there's the kind of the L to the left here. Now what we have on this particular is we have AY, and AY is down a value of 1/10. And what else do we have? We have that virtual couple, right? Now you might remember from our previous problem that we assumed a coordinate system as a function of x, so I have to do that again. We also assumed a moment in this direction, but now this is going to be the virtual moment due to an angle in AB. I'm sorry, that's BC. So I need to find this moment as a function of all that stuff. Well, that's not too bad. We've done this probably a few hundred times now. We're going to sum moments about the section we just cut. Make sure it's in equilibrium using right-hand rule. So starting with that, my internal moment, this virtual moment, is positive. Now remember, the theta just means it's generated by a moment. I've got that, and then what else do I have? I've got this reaction of 1/10 also creating positive moment. The force is 1/10, and what's the moment arm? X. And then what else do I have? I got this guy, which is negative. Oh, I did that wrong. This should be positive, right? Because about the cut, it's creating positive moment, right-hand rule. And the other one is negative, so that's -1. So there's all the pieces. So now my internal moment in this section of BC is just equal to, it looks like it's going to be 1 minus x over 10. Okay? Now let's do the other piece. So that'll be this cut, and we're looking at the right side. So let me draw the free body diagram for that. Now over here at D, we found dy to be 1/10 up. So I'll write that on there. Oops, not 20, 10. We also assumed in our previous work that we had a coordinate system going from right to left called x1. And our moment was positive in this direction. So we'll be consistent with that. But this is going to be the virtual moment due to the rotation in BC. And that's it. So the difference here is one has the virtual load and one does not. Oh, I'm sorry, the virtual couple. So again, using right-hand rule for our sign convention, we will sum moments at the cut, make sure it's in equilibrium. And what do I have? Well, according to this sign convention, that internal moment is negative. The moment to this 1/10 force is positive. So the force is 1/10, and the moment arm is x1. So now when I solve for the virtual moment in BC, I get x/10. Or, I'm sorry, x1/10. No, it's positive. Oops. So now I just have to match all these things together and see what my interval looks like. So now, EI times the slope at A is going to be equal to what? Let's go back and review for a second. So here is my real moment over this section of BC. With my coordinate system going from left to right, that'll be an integral from 0 to 5. So this will be the integral from 0 to 5 of the real moment, which is 6x, times the virtual moment, which is 1 minus x over 10. And that'll be integrated dx. And then we'll add to that the real moment over in this section, which remember I solved for with an x1 coordinate going from left to right. So that's going to start at 0 and also go to 5. So that's going to be another integral from 0 to 5. The real moment there is 6x1, and the virtual moment is x1 over 10, and that'll be dx1. Okay? Now before we dive into this, there's some interesting things here. You'll see there's a lot of terms in the integrand that look the same. In fact, this one is 6x times 1 minus 6x times x over 10. So that'll be a negative 6x squared over 10. And over here we have a positive 6x1 squared over 10. They basically cancel. So what are you left with? 6x. So this is really going to turn into just the integral from 0 to 5 of 6x dx. So this times this is positive, matches with this times this, which is negative, which matches with this times this, which is positive. They cancel. So you're just left with 1 times 6x. So that's pretty easy to do. I think even I can do that. So that just means we have 6x squared over 2 evaluated from 0 to 5, which is what? That's just 25. 25 times 6 is 150 divided by 2 is 75. Is that right?
Yep.
So this is going to be 75, and this will have units of kip feet squared. So to get the numerical value for theta A, I just need to divide by EI. So I've got my 75 kip feet squared, and I need to divide by E and I. E is 29,000 kips per inch squared. I is, the I value for BC is 900 inches to the fourth. And now I just have to convert this feet squared. So there's 144 square inches in a square foot. So again, my feet squared cancels, my kips cancel, and I'm left with inches to the fourth over inches to the fourth. So I have a dimensionless number, which is great for my angle. So what is that? It looks like it's going to be really small. Anybody get that? I don't have a calculator with me.
0.0004.
How many zeros before the 4?
3.
You got 6?
Oh wait, I didn't.
So anybody getting 3 zeros and a 4? Yep.
Yes, sir.
What's after the 4?
1 4.
Another a 1?
Yeah.
That's close enough.
Yeah.
So let's just say it's that many radians. Pretty small angle. It is positive too, so what does that mean? That means my original choice for the rotation, which was also positive. Where did it go? Oh, here it is. I assumed this was positive. That would make the structure rotate this way. It's true. That's the way it would rotate. That makes sense to me.
So, Dr. Ham?
Yeah.
So say where we found 0 moments in A, B, and C, D.
Mm-hmm.
If there was a moment for whatever reason, and we did the...
Well, then I have to do the virtual moments in here too, just like we did.
Yeah. But like when you found all that, you just get down to the bottom, you start writing integrals, you would have 4.
Right.
At the bottom.
Right. Okay. We'll stop there.